Cloud. All right, so this is the lecture number 4, and let me actually start from where I left last time before we begin the topic of today's lecture. So, so last time we concluded that any 2x2 matrix can be represented in this combination of outer products of vectors 0 and 1. Okay, and now I ask, what would I get if I consider a sum of diagonal components like this? So what would I get? So this UN cat and bra, they are basically the same vector, and they belong to the basis. Okay, so they are orthonormal. I can consider first a particular case for our 2x2 inner products that we just discussed. For example, for this case we have only two options here. So the term 0, 0, okay, and another one is 1, 1, and is 1, 1. So I remind you that 0, 0 is equal to 1, 0, 0, 0. So it's a matrix 1, 0, 0, 0. And the outer product 1, 1 produces the matrix 0, 0, 0, 1. Okay. And the result is, of course, 1, 0, 0, 1. So it's a identity matrix. Okay, and now I'm asking if I can, if this is the same true for the general case. To confirm that, let us consider the representation of any vector psi. It can be a dimension of more than 2, so it's a general case, and the conclusion will be rather general. So I decompose my psi vector by or over the basis. Let's call this basis UN, right? And the sum runs over, n from 1 to the dimension of the space. So we know that psi n in this formula is the projection of a psi vector on the corresponding basis vector. The corresponding basis vector, so it's something like this. So now let's go and plug in this formula to this summation here. So what would I get? I would get psi n, psi, and then this un, right? So now let me exchange the terms here. So basically I put this un in front. Okay, so what would I get? I get summation over n, and then un, then un again, and then psi. All right. And now I see and I compare the left and right sides of this expression. So on the left side I have plus psi vector. On the right side I have this summation of the outer products of all the basis vectors times the same vector, which means that this product must be equal to the identity matrix, right? So this way I get psi equals to psi. So this is supposed to be identity matrix. So I conclude that, and it's pretty important result. Sometimes, I mean, we're gonna use this one. So the sum of all outer products of the basis vectors is equal to the identity matrix. Okay. All right. So this was the last thing I was planning to discuss last time, last week. And so if you have no questions, let us start the second chapter. Chapter 2, and we call this basics of quantum mechanics, or quantum in general. Basics of quantum mechanics. Okay. Basics of quantum mechanics. And the way we will discuss the quantum mechanics, I mean, of course, at this point, I assume that you already heard about quantum mechanics and in the course of, I mean, basic physics or maybe other courses. And of course, I will remind you the things that we will need for this course, and we also will discuss some I mean, the things we will need in more detail. And the way I will represent this part of the course, we will use the approach of postulates, right? So the postulate 1, postulate 2, we will basically discuss this topic by parts, essential for them, for what follows. And we're gonna start with the postulate number 1. Postulate number 1. And it sounds like this. So the state of a quantum system is represented by a vector, or vector state, in the complex Hilbert space, right? So up to some, I mean, we already mentioned this or discussed, but now this comes as the very first postulate of quantum mechanics. So the state of a quantum system, of a quantum system, is represented is represented by a vector, vector state in the complex Hilbert space. Hilbert in the complex Hilbert space. So what it means? It means that if I consider a general quantum system, I need to describe this quantum system somehow, right? And to do so, I introduce a complex Hilbert space. Complex Hilbert space. We already mentioned that the Hermitian conjugation, Hermitian operator has two very important properties. The first one is that the eigenstates form the basis, right? And eigenvalues give the the values that the system can take. And for example, to construct this Hilbert space, I can use the eigenvectors of a Hermitian operator. Okay, so I have this space, and let me name this basis vectors are as for example, this is 1. Let us start from 0. So this is 0, this is 1, this is 2, and I of course can get more states like this. So all these basis vectors are orthogonal. Okay, and for example, this could be state n, etc. And and let's suppose the state of my quantum system is given by a vector psi. This is basically what is formulated in this postulate 1. So the state of a quantum system is represented by a vector in this Hilbert space. So this pinkish state is the state of my of the quantum system. And this state can rotate, evolve in this Hilbert space, and this, and then I can find the projections of this psi state on every basis vector. Okay, and these projections give me the numbers, the complex numbers c sub 0, c1, c2, c3, cn, etc. Okay, and as we discussed last time, probably we can represent this psi vector, this quantum state, as a superposition. So now I say this word, right, for the first time, I guess. Superposition of all the projections of the psi vector in this Hilbert space on all the basis vectors. So it's gonna be C0, 0 state plus C1, 1 state plus etc. And in short, it is equal to the sum of over, n, Cn state n. Okay, so this is the superposition of states. Okay, so if this psi vector doesn't coincide with the basis vector, so it always represented as a superposition of all possible states. Okay, so let us consider a simple example. Example 1, for example. A particle like electron passing through a slit in a screen, a slit. Okay, so this is famous experiment usually considered in the when we discuss the history of quantum mechanics. So basically, the story is like you have an electron or a number of electrons, and the electrons, they pass through a slit in a screen. So let me draw this screen here. Okay, so this is the screen with a small slit, with a small hole. Okay, and so the experiment tells us that even if I know the state of this electron before the slit, was denoted by psi sub naught, okay, after the slit, the state of the electron is unpredictable. Okay, so the particular state is unknown. We can put the detector and measure which way this particular electron scattered to. But before we do this measurement, we don't know which way the electron, which way the electron goes after the slit. And for this, if we name these paths, these waves as zero way, 1 way, 2 way, etc., up to n way, we have to take into account all of these states. Okay, and if I name this state 1 after the slit, I have to write this one state as a superposition of all possible states n. Okay, yeah, all possible states in the system. Okay, so this is the first postulate of quantum mechanics. If a system can exist in several states, one has to take into account all these states, like take the superposition of all these states, if we don't measure the system. After measurement, as we will discuss in a while today, after the measurement, the system collapses to one of these particular states. 1, 0, 1, 2, etc. But before measurement, we have to consider the system to exist in all states simultaneously. And this concept, sometimes it's known as quantum parallelism. Okay, that a system lives in all the states simultaneously before we measure the system. Quantum parallelism. And this is kind of experimentally proven fact today. Okay, so let us consider a more more useful example, particularly for our course. So the example 2. So we consider two-level system. Two-level system. Two-level system TLS, or it's known as a qubit. Okay, so again, this word qubit, two-level system. So two-level system gets only two levels or two states. Okay, so this is the state 1. I just draw this schematically. So this is some state 2, state 1, state 2, and the system can exist in both of these states. So it kind of evolves or I mean exchange between state 1 and state 2. Okay, and as we discussed last week, we can name the state 1 as a 0 vector with components 1, 0, and the state 2 we can name it 1. Maybe it's not good naming state. Let me call this state 0 and state 1. Okay, then state 0 is represented by vector 0. State 1 is represented by vector 1 with component 0, 1. Okay, and this superposition principle uh, dictates that we write the psi state of the entire two-dimensional, entire two-level system, entire qubit, as c sub 0 vector 0 plus c1 vector 1. Okay, yeah, and this is known as the qubit state. Qubit state. Very simple. All right, so we have two basis vectors, and we represent the general psi vector in this state, and the components c sub 0 and c1, they give us the projections on the each vector. I've got a question in chat. Let me read the question. I'm sorry whenever it's not too instructive to do so. Could you explain what bracket notation again? Come on, we discussed that last week probably, right? I forgot what you said and I'm feeling okay. So bracket notation. Let us go back to where we introduced that and where we discussed this. So the first time we introduced the bracket notation is this Dirac notation over here. Okay, so this is Dirac notation for vectors. So Dirac notation for vectors is particularly useful for quantum, because in quantum all vectors are complex valued. Okay, and the way you write the inner or outer products of two vectors, you need to take this complex conjugation and transpose. So, and in terms of Dirac notation, the difference between the two is the ket and bra. Okay, so the ket vector, is the vector of, it's a column vector of components, right? A, B, C. In two-dimensional is A and B. Bra vector is obtained from ket vector by taking the Hermitian conjugation. Which means complex conjugation and transposition. Okay, and transposition means that the column becomes a row, like here, for example, right? The state 1 becomes the row vector 0, 1, and the column is vector, is a column vector. Oh, sorry, the ket is a column vector. And if components are complex valued, you also need to take the complex conjugation. So it's not only for quantum mechanics. It's like it's whenever you deal with linear algebra of complex valued vectors. And we discussed this in more detail last week here when we introduced two-dimensional Hilbert space. Okay, because in Hilbert space the vectors are complex, and we need to like keep track of this complexness. For example, we always need to take this complex conjugation. Okay, so the ket vector is this one. I take the Hermitian conjugation of the ket vector, I get bra vector, and then the inner product of the two is the scalar, like this. The outer product is the matrix, like this. And yeah, so this ket and bra just another way and a useful way to write vectors. Okay. Yeah, you're welcome. Yeah, of course, if you have any questions, just unmute yourself and ask, or in chat. All right, so this is the qubit state. Qubit state is the combination like this. The C element 0 state 0 plus C1 state 1. And I mean, of course, we can rewrite this, substituting this 0 and state vectors by the actual vectors. So it's going to be C0, right? And then vector 1, 0, and then plus C1 vector 0, 1. Okay, it's the same thing. Or I can multiply the coefficients by the components of the vectors. So I get C0, 0 here, plus 0 here, C1 here. And I can make the sum of this. So I get C0, C1. Okay, so it's very simple. It's just a ket vector of the projections of the psi vector, this psi state, on each basis vector. Okay, I remind you that C0, for example, is nothing but 0 psi, and psi1 is similarly 1 psi. So projection of psi on the 0 or 1. Okay, I suppose this is supposed to be clear now. So this is the first postulate. Let us consider the second postulate number 2. And it gets a special name of Born rule. Born rule. And it says that the coefficients, these coefficients C sub 0 and C sub 1, they correspond to the they connected to the probability of measurement of the system. Okay, so let us write this. So the coefficients C sub n, right, in the expansion are the probability amplitudes. So there is probabilities. Probability is a number, right, between 0 and 1, and the larger probability, the more I mean, the result is more like expected, right? And when you toss the coin or a coin, you get one side or another side, so the probability of getting either one is 0.5. So this is probability. Probability amplitude also corresponds to probability, but you need to do something else to get the actual probability. Okay, so for now, let us write like this. So this coefficient Cn are the probability amplitudes, amplitudes of finding the quantum system in the state n, in this state n here, of finding a quantum system in state n. Okay, so in state n. So example for the qubit. Example qubit. As we just discussed, so the general state of a qubit is given by the superposition C0, 0 plus C1, 1. Okay, this superposition of two states. And if I multiply this expression by bra, for example, 0, right? What would I get? I would get 0 here, then psi, then equal to C0 is a constant. I can take it out from the dot product. And then I get 0, 0 plus C1, likewise 0, 1. Okay. And since these vectors are orthogonal, this guy equals to 0, this guy is equal to 1. So I get the expected result that C0 is equal to 0 psi. And likewise for the Cn, I would get 1 psi. Projection of the psi vector on the basis vector, as we discussed this several times already today. Okay, but this result, this number, is a complex number. And the complex number cannot represent a probability, because probability is a real number between 0 and 1. So how I get the actual probability? To do so, I need to take the absolute value of this complex number. So I take the absolute value squared, which is C0, C0 complex conjugated, okay? And it's equal to absolute value 0 psi squared. Okay, so this is already real, and it gives us probability of getting in state 0. Okay, of getting state 0. And likewise for the state 1, I get this probability C1 complex conjugated is equal to 1 psi squared. So it is also real, and the probability of finding state 1. Okay, so let me return to this picture of two states, 0 and 1, and the system exchanges between 0 and 1 state, and measuring one of these states, either 0 or 1, or measuring this system, I can find this system either in zero state, in the state 0 or in the state 1. Okay, and the probability of finding the system in the state 0 is given by absolute value square of C0. And likewise, the absolute value squared C1 gives us the probability of finding the system in the state 1. Okay. And we have only two options here, either 0 or 1. And we know that the total probability must be equal to 1, right? 100%. That means that C0 squared plus C1 squared must be equal to 1, which means finding a system in either 0 or 1 state. Yeah, so this is 100% of probability. And of course, in a general case, the same is written this way. So for more than 2 terms. Okay, so it's we say that the states must be normalized to the probability 1. Okay, so this is postulate number 2. Let me maybe summarize this. So the postulate number 1 says that a quantum system is represented by a vector in a Hilbert space. So this is already quite unusual, right? Because, for example, in classical mechanics, we consider a system like a particle moving somehow, and we assign a coordinate and the momentum, velocity to this particle. And then we know we have this Newton's law that describes the motion of the particle imposed to different forces, etc. So this is the way how we describe a classical system. In quantum system, it's completely different. I mean, the description. And this is because the experimental results, the experiment says that we cannot assign a particle the position and the velocity in the same time, right? This velocity and position, or momentum and position, they are not defined at the same time. We will discuss this later today. The point here is that this description based on like classical variables is not applicable to quantum system. Okay, and this is first. And second, and also quite important, is to understand that a quantum system is not just small particle like electron, photon, like this. A quantum system can be a large system. Okay, for example, today's quantum computers, they are like very large, the size of I don't know, like a room. And even though these systems, these quantum computers, they are large, they are bulky, they are in the quantum state. So for the quantum computer, you don't have coordinates or velocities, momentum. You actually don't work with you don't work on the single particle level, right? Instead, you have a system, and the system gets currents of many electrons there, but this system behaves in a way that you can describe this state by just one vector, this psi vector. So this psi vector can include a state of a large quantum system, like a large bulky quantum computer. Okay, so it's already here. It's already here. And the first postulate says that we can describe the quantum system introducing this psi vector, and then using the superposition principle of states, we can decompose this state by projection this vector, this psi vector, on different basis vectors. Okay, and these basis vectors can be different because usually these basis vectors are the eigenvectors of a Hermitian operator, some sort of Hermitian operator. For example, energy. Okay, so we will discuss that also today. The point here is that the psi vector, this psi, is a state of a quantum system, and it's given. But the basis, this basis can be rotated, can be transformed, can be changed, and also the probabilities also can change depending on what basis you work in. So it might sound like a little complex, but you will get it. You will get used to all this terminology. And second postulate says that we have this Born's rule, and the Born's rule says that the absolute value squared of elements of this expansion, this C0, C1, etc., they give us the probability of finding a system in a corresponding state. Okay, so I measure the system. For example, I have this computer. The computer gives me some output, and I measure this output. And this result, the result of this measurement gives me these numbers, C0, C1, absolute value of those. And this way I can basically get some information of the result. I can get the result, I can get the statistics, etc. We'll discuss that later. But now let us go to the postulate number 3. Postulate number 3, which says that the physical observables, okay, so observables are the quantities that we can measure in experiment. Okay, at some point when people develop quantum mechanics, they realize that there are two kinds of quantities we work with in physics. One is observable, the thing that we can measure and observe in the experiment, and non-observable things. And so here, basically quantum mechanics is talking about observable things, the things we can measure in experiment. So the physical observables, physical observables, physical observables are represented by Hermitian operators, by Hermitian And I remind you that Hermitian means if I have an operator and I take dagger, Hermitian conjugation, right? The complex conjugation and the transposition. And if after this operation, the operator or matrix coincides with itself, then the operator is Hermitian. So physical observables are represented by Hermitian operators. Okay, why so? Because as we discussed and proved maybe on the first lecture, that Hermitian operators, they have real valued eigenvalues. Okay, real eigenvalues. And since all physical observables, they are real, because we can measure them, they are supposed to be real. And since they're real, we need matrices that have real eigenvalues to represent the physical observables. Okay, so we use Hermitian operators to represent physical observables. So let us write this also the following way. So the classical quantities, in classical physics, we have position, we have momentum, energy, right? And in quantum mechanics, these quantities are promoted to Hermitian operators. Okay, so the classical quantities like position R, momentum P, energy E, etc. are promoted to Hermitian operators. To Hermitian operators. Hermitian operators. They got the same letter, except maybe for the energy. The same letter, but this small hat on top, like this. So this is the operator of position or momentum, operator of radius vector, momentum of operator of momentum. Operator of energy gets a new letter H, which is I mean the first letter of Hamiltonian. It's I mean because that's due to because of the importance of this operator for quantum, etc. Okay, so classical quantities are promoted to Hermitian operators in quantum. And eigenstates, so operators can be represented in matrix form, and matrices have eigenstates and eigenvalues. Okay, and the eigenvalues of the Hermitian operators, they form the basis for the Hilbert space, right? Eigenstates or eigenvectors, they form the basis of the Hilbert space. Okay, this is about eigenstates and eigenvalues. Eigenvalues basically they form the values that the observable can take. So the eigen values form the or values that observable can take or acquire. So this basically means that anything you measure, that the value that you measure, for example, you measure energy, okay, and the result cannot be any number. The result must be one of the eigenvalues of the corresponding operator. If we measure energy, the corresponding operator is this H operator, Hamiltonian, and the result of this operation, of this measurement, must be one of the eigenvalues of this operator. Okay, so the result is not any number, it's only one of the allowed numbers. Okay, so let us consider one simple example here. Example, Hamiltonian of a general qubit. Hamiltonian of a general qubit. I heard some noise. Do you have any questions? Daniel? Okay. Hamiltonian of a general qubit. Okay. So how we would write Hamiltonian of a general qubit? And let's suppose we know, or we can measure the energy that this qubit, this system, can acquire. So we measure the energy, right? And the classical energy is given. Energy is given, and for this energy is represented by the Hamiltonian in quantum mechanics, right? So this H says Hamiltonian. And for particular Hamiltonian, we can solve the eigenstate and eigenvalue problem. I remind you that this problem is given by this formula, the operator, then vector, and if this psi vector is the eigenstate, then it's just multiplied by eigenvalue. Okay, if you don't remember this, I refer to maybe the first lecture in our course. So this is eigenstate and eigenvalue problem, or for formulation of this eigenstate and eigenvalue problem, EEP. Let's, for brevity. So I solve this equation, and solving this equation gives me the eigenstates, right, which is 0 and 1. For the qubit, we know that the eigenstates are either 0 or 1. So this is eigenstate. Okay, and eigenvalues. Eigenvalues are the energies. Eigenvalues are the energies. So it's energy that the zero state has, or energy that the first state gets, the E0, E1. So these are eigenvalues. Or energy. Um, and first of all, we see that in terms of a qubit with two different energy states, the spectrum is a composition of the two eigenvalues, right? So the values E0, E1, they form spectrum. So the spectrum is the basically the all set of possible energy states. So this is spectrum, and in this case the spectrum is discrete, right? So it's a discrete or quantized spectrum. Discrete spectrum. So the spectrum is discrete. Later today we will also mention that or discuss that the spectrum can be actually continuous. But in this particular case, the spectrum is discrete. Another example of a system with discrete spectrum is a hydrogen atom, right? Notoriously known hydrogen atom with separate energy levels. So this it also gets discrete spectrum, or the spectrum is quantized. So that's why the name for the quantum mechanics, the quantization. So when something gets quantized, it means that this system gets isolated, allowed isolated levels or states. That's why it's known as, that's why this word quantum. So let's suppose we found this, or we measured this zero state energy and one state energy. Quite often we represent them in an energy diagram like this. In this case, we have only two energy states, and usually the state 0 is the lower energy state. State 1 is the higher energy state, so it's E0, E1, okay? And the system can transit between or jump between 0 and 1 state like this. So for example, if we take a system in the 0 state, we can impulse it, we can pump it somehow. It depends on the concrete geometry or type of the state. We can excite the system to the state 1, and vice versa when we release the system and allow it to behave on its own. Usually the system evolves in a way that it goes from the excited state to the lower state. Okay, and again, I remind you that the state of the system is given by this superposition, the C00 plus C11. Okay, and finally, in the energy representation, I can write the Hamiltonian of the system simply as a matrix with the energies on the main axis. So it's a E0, zero energy, E1. Okay. So it's supposed to be clear. If not, so the process, or the way we find the eigen values of any matrix, right? We diagonalize the matrix. And in this case, or in this formula, this matrix is already diagonalized. And on the main axis, it gets E0 and E1. So these are the eigenvalues of this matrix. So this matrix represents the Hamiltonian in the energy representation, which means that like if we describe the system in energy representation, if we describe the system, the qubit in energy realm, or representation in the energy representation. So again, let us consider a big, large system like quantum computer, right? So it's a really large system with many wires, and of course each wire contains billions of billions electrons interacting, etc. And we could try to write the energy of such a system, taking into account all the energies from all the charges, particles there, and that could be a coordinate representation, but that would be so difficult and so complicated. But at the same time, we, for example, know that this large entire system can take either state 0 or state 1, right? Or one particular qubit in the quantum computer. It can get 0 state or state 1. And we know the energy of either 0 or 1 states. And in this case, we can write the Hamiltonian for the anyhow complicated system this way. So usually this energy representation is much more feasible, much more much simpler for formulation and for the studies. Okay. But we, for the completeness, we also need to describe the case with a continuous spectrum. Okay, so let us consider another example. Example 2. Coordinate representation. Coordinate representation. So the coordinate representation is something that you start, like when you start reading about quantum mechanics, usually the authors start from coordinate representation. But since it's not useful for quantum computing, I gonna formulate or summarize this part like very quickly, very briefly, and the form of an example rather than another chapter or so. So it's kind of an example, less useful for quantum computing, but very instructive for understanding. Okay, so the coordinate representation, also operators of coordinate and momentum, operators of coordinate and momentum, and also let's add the continuous spectrum. Continuous spectrum. Continuous spectrum. So I said that when you read books on quantum mechanics, usually authors start with formulation quantum mechanics in coordinate representation. And the way they do that, first they discuss different experiments, like that experiment with a slit or double slit experiment, etc. Like for example, when you read these books by Feynman, right? Feynman's lectures on physics, they all formulate. They start from historical introduction, the results of famous experiments, and then they came to the concept known as particle wave duality. So you probably heard about this particle wave duality. Like usually it's formulated in a way like asking whether electron is a particle or a wave. Well, sometimes it behaves as a particle, sometimes it behaves as a wave, and in fact it is actually like wave particle, right? It's not particle, it's not wave, but depending on experiment, depending on the parameters, it behaves either like a wave or the particle. Okay, and in the situations when it behaves as a wave, we describe this wave in terms of the de Broglie wave function. Okay, so let me write this down this way. So the particle in free space is described by de Broglie wave function. Particle in free space is a de Broglie de Broglie de Broglie wave function. So the Broglie wave function is nothing but just plain wave, right? So let us also write down this in red. So now I'm considering a particle in free space, like electron in free space, and the way I describe this, I introduce this wave function psi, and is equal to some amplitude a times e to the power of I k r. Okay, so it's a plane wave. De Broglie equals to plane wave. Plane wave. So it's also kind of a postulate that a free particle in a free space is a plane wave. Okay, the A here is the normalization amplitude, normalization amplitude. R is a position. R vector is a radius vector. Radius vector or position. Position, some coordinate in space, right? And K is the wave vector. Wave vector. And for the free particle, it's connected to the momentum through this simple formula. The momentum of the particle is equal to the wave, the module of the absolute value of a vector, which is wave number. So absolute value of wave vector is a wave number. Okay. And there is a simple formula that connects the wave number and the momentum. So the momentum is equal to wave number times h bar. Okay. And this is the place where in all textbooks the Planck's constant appears. Okay. So this h bar is a Planck's constant. Planck constant. So Planck's constant is a very small number, and that's why the quantum effects, they so weak and like difficult to detect, to observe. Okay. And yeah, I guess it would be nice to make a sketch at this point. So in the real means space, in the geometry or coordinate system, I have a particle that moves from left to right, and so let me draw this plane. So this green line, it represents, let's actually write, let's draw the plane. So this plane corresponds to the to the front of the plane wave. Okay, and this front moves in space like this with the wave vector, like this. And this is of course x, y, and z coordinate system. And the radius vector, the position, is given by this radius here. Okay. So this is how it looks like. So we describe a free particle in free space using this de Broglie wave function, which is nothing but the plane wave, nothing but plane wave. Okay. And now we need to find or introduce the operators for the coordinate and momentum in the coordinate representation. So the coordinate representation means that our psi vector is a function of of coordinates. All right. So in coordinate representation, the psi vector is a function of coordinates x, y, z, or r. Okay. And in order to find the eigenstates and eigenvalues of the first operator, of the radius or position operator, we need to solve this eigenstate and eigenvalue problem, right? This double EEE problem, which is given by the the radius vector operator times psi vector, which is the function of coordinate. Okay, and as an eigenvalue, it's supposed to give me like coordinate in space, which is literally any number, right? A coordinate can be any, especially in free space. So I'm gonna get the coordinate itself, the radius vector itself, and times this psi vector or psi function. Okay, so I conclude from here. I conclude that the operator of the radius vector is equal to the radius vector itself. And it makes sense because, I mean, there is a theorem, or I mean, it's as a fact that the operator of a quantity in its own representation coincides with itself, with the physical quantity. For example, in the coordinate representation, the operator of coordinate is just coordinate. In the energy representation, the operator of energy is just energy, as we just discussed for the qubit, right? Okay, so in the coordinate representation, the operator of coordinate is just the coordinate. So what about the momentum? So what about the momentum? Again, we formulate the double EP problem, eigenstate eigenvalue problem. In this case, it's supposed to be like, let me write this in blue. The operator of momentum times the psi function of coordinate is gonna be equal to the eigenvalue of momentum, which is momentum itself, times the function of coordinate. Okay, so in this case, I cannot say that my momentum is just equal to momentum, but but if I use the fact that for the de Broglie for the free particle, the de Broglie wavelength is just the plane wave, right? I can substitute for the psi and and get the following. So I'm gonna get the operator momentum, then e to the power of I k vector r vector is going to be equal to p e I k r. Okay, and again the k number here is the momentum over Planck's constant. Okay, so my momentum operator supposed to be, let me rewrite this so you can see it nicely, equal to, I substitute for k, so I get this p e to the power of I p over h r. Okay, right, so I get this p here and here for the exponential function. It means that the momentum operator supposed to be the coordinate derivative over r, okay, with some coefficient. So we can find this coefficient. So let us make an assumption that the momentum operator is equal to some lambda, some constant that we're gonna define now, and times nabla. Okay, so nabla is the derivative by r vector, or d over dxi plus d over dyj plus d over dzk. Right, so nabla operator, or just derivative by r vector. Okay, so it's alpha nabla, or the same as alpha d over dr vector. Okay, so now if I apply this momentum operator on my de Broglie's function ikr, so this is exponential function, so I get just e to the power of ikr, right? And times ik, because of the chain rule. And now I substitute for k this p over h bar, k r, and then times imaginary unit p over h bar. Okay, and now I substitute this to this eigenstate and eigenvalue problem. So what I get, or actually I see that if I write the operator of momentum in minus I times h bar, because they will cancel out, and then times the nabla, it's gonna be my operator, right? Because this way the h bar cancel out, imaginary unit cancel out, and I get p, the momentum. All right, so this is the operator of momentum operator. But this is for the operator of the vector momentum. We can write the same for the components. For the px operator, I get minus imaginary unit h bar d over dx, right? Basically the x component of, where is it? Yeah, here. X component of the nabla. Py, I get minus I h bar d over dy, and finally for the z, it's gonna be minus I h bar d over dz. Okay, so these are the operators of momentum. Oops. Okay. And yeah, let's also note that the R operator and momentum operator, they have continuous spectrum, right? So in contrast to hydrogen atom or a qubit, the position of a particle can be any, so it can take any number. So the spectrum of this operator is continuous, and the same for the momentum. If the particle can go in any direction in space with any velocity, effectively velocity, then the spectrum of momentum is also continuous. Okay, so in quantum mechanics there are two types of operators. The one type gets the discrete spectrum, like energy spectrum, and another type gets continuous spectrum, like coordinates, momentum. For the quantum computing, we will focus mostly on the discrete spectrum, and this part is rather for the completeness. So we mentioned this de Broglie wave function. We mentioned the wave-particle duality, and we also mentioned or discussed how the momentum and coordinate described in this coordinate representation. Okay, so that was postulate number 3, and we go to postulate number 4. Postulate number 4. So by the way, if you dig to the literature, to the textbooks, you can't find this representation of quantum mechanics through these particular postulates. Okay, so it's gonna be different and long discussion, one part and second part, and I think the best and the most is the easiest and the most quick approach to introduce quantum mechanics is using this postulate approach. Okay, for the same reason, no need to remember what is first postulate, what is second postulate. I'm just trying to give these portions of information in a way, like in the most in a way that you understand how it goes. At this moment, probably you don't understand everything in total, but you will get it, and also you will get another homework assignment where you will practice these things. So you will get it. All right. So the postulate number 4, I give it a title: projective measurements. Projective measurements. Projective measurements. So before discussing projective measurements, let us make a note on what is a measurement, right? So the measurement, like if I have a quantum system and I need to define the state of a quantum system, I obviously have some sort of a apparatus, a device, or some equipment, right, that works as a detector. So I bring in contact this detector with the quantum system, and detector shows me some information like energy of the system. But of course, this detector affects the state of a quantum system. Okay, and the way it affects on a quantum system is known as projective measurement. So the measurement is interaction of a quantum system with a classical system. Interaction of a quantum system with a classical one. Classical system. And we call this classical system as a detector. Detector or equipment. So actually any type of interaction of quantum system with classical one is an act of measurement. In some books or maybe popular lectures on quantum mechanics, you can find like statements like, oh, the result of measurement affects the future, and the effect of observer like experimentalists, the presence of experimentalists affects the behavior of quantum system, like, or in other words, it like affects the future of the system. But in fact, it's not the case at all, because in quantum mechanics, any interaction of a quantum system with classical system, like of any kind, any classical system, is known as an act of measurement. Okay, so it's more broader thing than in classical physics. Okay, and as a result of this measurement, the state of a quantum system collapses to one of the possible eigenstates. And this is important, so let's write this down. So in result, the state psi, we denote this by psi vector ket of a quantum system collapses to one of the possible eigenstates of the possible quantum, possible eigenstates. Or basis vectors. Okay, so we already touched upon this, and just let me state it once again. So suppose before the measurement we have a quantum system described by psi vector in the Hilbert space, and because of the superposition principle, we can write this state as a superposition of projections on all basis vectors, right? Psi n. So psi n is the basis vectors, Cn is the projection coefficient on the corresponding basis vector. And what happens, and this is the result of experiment, or actually a lot of experiments. So this point is still under debate, and a lot of discussion in the literature, you can find recently published papers on the nature and the philosophy of this aspect of quantum physics. But the experiment tells us that when we measure this state of the quantum system, it collapses. So it's a measurement. It collapses to one state from the basis states, from the basis vectors. Let's use blue. So in result, I get just one state. So before measurement, I have a superposition of many states. After the measurement, because of the classical system, this setup, this detector affects the quantum system, the quantum state collapses to just one particular state. Okay, and we can't predict which state it will collapse to. But what we can do, we can tell the probability. So this measurement will collapse the function to psi m with probability psi cm squared. Okay, so the absolute value of this Cn give us the probability of finding the quantum system in the state psi m. And when we measure the system in the psi m state, the system collapses to the state and lives there until it gets the state of the system becomes the superposition again because of other processes. Okay, so it's a little bit unusual, but this is the way how the quantum systems work. And anytime, like quantum computer, right? We will discuss that, but the quantum computer does some operations, and in the output there is a array of output qubits. Okay, and each of these qubits get the superposition of states, and then we measure each qubit, and that measurement, and as a result of that measurement, we found the qubit, each particular qubit in a particular quantum state. And after doing this several times, we can get this coefficient Cm, for example. This is one of the approaches. Okay, so we can get this Cm, and this distribution of Cm squared, these coefficients, will be the result of the computation. Okay. So let us finally, maybe the final point for today, state the following. So the projective measurements. So yeah, by the way, this name projective measurements, right? This projective means that after the measurement, the state is projected on one of the basis vectors. That's it. So that's why projective measurements. And these projective measurements can be represented by projective operators, also known as projectors. Projective measurements can be represented by projective operators. Or projectors. Projectors. So these projectors equal to the outer product of two vectors of the same vector by itself, of vector state. For example, in this case we use this psi m as the final state. So let's also use this psi m here, outer product psi m, like this. Okay, so this is the projection operator or projector. Why it is projector? Well, if we take a state psi, just arbitrary state, and we apply on the left this projection operator like this. So what we get psi m, psi, right? Okay, and on the other hand, this is equal to Cm, right? This complex coefficient that describes the probability of finding the state in the state psi m. And this is constant, so I can write this the first place, Cm multiplied by psi m vector. Okay, so the result of application of projector on any vector in this space is the psi is a vector in the corresponding state. Okay, so initially you had this psi vector here, and then you get psi m vector in the output after action of this projection operator. Okay, so I feel that that's enough for today, and next week we will continue discussing the basics of quantum mechanics. In particular, we will discuss the spin. Right, spin is important. Pauli matrices, and we will start discussing the time evolution of quantum systems using the Schrödinger equation, etc. So this is all for today. Thank you. Let me stop the recording.